going to find the first parody on CERN. We're going to highlight the false stance. I never heard that term.
You've never heard that term?
Oh my goodness.
Okay, shall we start?
Guess can do.
Just the spot.
I know
We
you're
finished in
George.
the middle of this proof,
In the proof, that's it.
but it's good to remind ourselves what we're actually proving.
Don't believe that. Got minutes to recap.
And what we're proving is that every subgroup of a cyclic group is cyclic.
Yeah.
Which is
That's why I did last lecture.
She did that 3 times, it was so funny.
Because if I was going to drop out and retrain that, or maybe help.
The way we're proving it is, well, G's cyclic, okay? So that means it's generated by a single element. And H is a subgroup, but we want to show that H is cyclic. So one trivial case is where H is just a trivial subgroup with only the identity. And if not, then we found the smallest m such that the nth power of the generator, or the A generator of G, so of the generator we picked, is in that subgroup. Okay. So m we selected so that A to the m is in H, but A to the anything smaller than m and bigger than 0 is not in that subgroup. So that was our choice of m. And now what we want is to show that A to this particularly carefully selected power m generates the whole subgroup. And if there's one element that generates the whole subgroup, that means that it's cyclic by definition. So this remains true. Now, okay, so well, when you're proving that something equals a set, it's like a set. Right? This is some elements of the group G, and this is a set. So every time you're proving that the 2 sets are equal, the usual way of proving it is you prove both inclusions. So this is a subset of that, and that is a subset of that. That is the usual way how you're proving that the goal is to prove that 2 sets are equal. So here in this case, and quite often, just like in this case, one of the inclusions is very simple. So because A to the m is in the group is in the subgroup H, and everything generated by A to the m also has to be in the subgroup H, because otherwise it wouldn't be so. So obviously, this is a subset of H. Okay? So we need to prove the other inclusion. So we need to prove that H is also a subset of that thing generated by A to the m and then the and prove that H is a subset of A to the m. How does one prove inclusion? Well, look at any element of H and prove that it is also in the other set. That proves that definition of the subset. So we take some element H dashed, which is in the subgroup H, okay, and we want to show that it is A to the n to the something. Okay, and that will show that it's in the brackets of A n. So we want that H is A to the n to some power A. won't say P, I'll say N. For some integer N. Yeah. Because this statement is exactly the definition of being in this bracketed A to the N. Sorry, I changed it to N because P somehow suggests that it's a prime number. I don't want to claim that it's a prime. H dash is because H is a subgroup of G. We started with that assumption. And H dash is in H, then it's also in G. And G is generated by A. So H dash must be some power of A, because it's in G and G generated by A.
Is that less than or equal to?
Yeah, that means a subgroup. But you could write the subset as well. It doesn't matter in this case. So for less than I write when it's a subgroup, which means that it's a subset and more. And C, as we called it yesterday.
What is it called? Does that have a name?
It's called the subset.
Is that a subset?
Yeah, so that means a subset. Well, there are different conventions. Some people write just the C without the line for a subset. But I write it with the line, which means like it can also be equal. And if I don't write the line, then I mean it can't be equal.
It's a subset.
Well, it's like this is greater than, and if the line is there, then it's greater than or equal to. So in the same manner, I use this for a subset, which can be the whole set.
Just without the equal, it's probably a subset. Well, it's not equal.
Yeah.
Yeah.
Okay, well, okay, so we've got this now.
For a minute.
Now we can use something that you probably know from elsewhere, either fundamentals or number theory, which is division. Secondary school, maybe, which is division with remainder, and so division. What division means is that K can be divided by 1 by 1 to divide it with by M. So K can be divided by M, and I get quotient Q and the remainder R. And I want the remainder is always 0. Can be 0, but must be less than n. So if you're dividing by 7, then the remainder is 0, 1, 2, 3, 4, 5, or 6. That's the meaning of this. And what's next? Okay, so then A to the K is using this division A to the M Q plus R, which is A to the M to the Q times A to the R. Okay, and this is H to the Q oh, I forgot to say something that's in the okay, no. So it's A to the N. Oh, I've already written this. Okay. stop. Now, what we had is this element, A to the n, is in the subgroup H. And because that's how we selected n. And so A to the n to the q is also in the subgroup H because H is a subgroup. And A to the k is also in the subgroup H because that's how we selected A to the k. Okay, so this is in H, this is in H, so we can divide in a group. So we could multiply this by the inverse of this element, we would get that A to the r also must be in H. Okay. So now A to the k is in the subgroup A to the n. The q is in the subgroup, so also A to the n minus q times A to the k, but the times is the group times. This is A to the r, is also in the subgroup. Okay, but A to the r is in H. So what can we conclude? The first line that I've left on the screen, that's giving you the clue. Can R be in this set? No, because R is less than n, and n was the smallest number in that set, and R, so R can't be in that set. So R must fail to satisfy either this or that. Okay, this it does satisfy, as we've just shown, so it can't satisfy this. So necessarily R has to be 0. Joke perhaps in the notes, but just it. Well, now if R is 0, that means that therefore, when we look at our element H dash, which was A to the k, which was A to the n to the q times A to the r. Now we know R is 0, so this is just A to the n to the q, because then A to the 0 is the identity. And so this is in the subgroup generated by n, and that's the end of the proof. Okay, end of magic. Any questions? Does it make sense to put together like this? If you can't quickly process it now, we will have to go on and process it when you get there. But this is the essence of it. So again, we want to show this equality, then we're showing two inclusions. Remember this trick, it's a very common, ubiquitous idea in proving successfully.
We prove that every subgroup has a generator overall.
Every subgroup of a cyclic group.
Of a cyclic group.
Yeah, has a generator. So it's also cyclic.
I might write that because I'll forget what this actually means.
Yeah.
When.
That was yesterday, so I can't blame you that was it. I didn't remember myself. Okay, so that's that. And there's a corollary. You've probably come across this word with Killian.
Which one?
Coral.
How can I have to say it out loud?
Coral. Or Carol.
Laurie.
411.
Say Carol and Laurie at the same time.
Which says that all the subgroups
Coral. Lorry.
Cam.
Calling
are
down later.
said are exactly N Z. Or non-negative. Why is that?
Oh, wait.
Okay.
Each one generates another cyclic subgroup, and because there's only the whole integers, if you go from n0 to whatever, that's all of the groups.
Okay. So Z is a cyclic group, as we said yesterday, generated by 1. Okay. So all its subgroup must be cyclic. So to find all the subgroups, you just look at all the elements of that and look for each of them which subgroup it generates, and like this you will get them all. That's what this theorem also tells you. Any cyclic group you get, if you want all the subgroups, you know they will be cyclic. So just look at every element of the group and which groups which subgroup it generates, and you'll get them all. Okay, so so the element 0 generates 0z, the element 1 generates the whole z, 2z, and so on. And the negative numbers, they generate the same as the positive numbers, so there's no extra subgroups there. So -3 generates the same as 3. That's the corollary. Okay. What else? We're getting very close to just want to do the complex. Okay, I'll start a new page. Because
Oh,
okay, there's a proposition. It says that if G is a cyclic group of order n, and A is a generator of G, then the K's power of A is the identity if and only if K is a multiple of n. Okay, if k is a multiple of n, well, first of all, a to the n is the identity. Because a generates the group G. So it has to run through all the elements, a to the k has to run through all the elements of G, and then it lands on the identity, and then it starts cycling over all the elements again. So that's where the cyclic group, subgroup comes from. So the powers of this element just cycle through all of them, and then again, and then again. Okay, so so if n divides k, then a to the k is a to the n of some s, because k is a s multiple of n, let's say, which is e to the s, which is e. Element of s. That's one direction of the proof. And the other direction, if a to the k is e, the identity, then we can divide k by n, and we get k is n times q plus a remainder, again, division. And therefore, a to the k is a to the n cubed plus the remainder, which is a to the n to the q, a to the r, which is a to the r. Now we have the same trick as before. So, so a to the k is the identity as we're assuming. Okay. So this is the a to the r is also the identity. And if a to the r is the identity, but r is somewhere between 0 and n minus 1, because it's the remainder, well, a to the anything smaller than n can't be the identity. So because a generates the whole group, the smallest n, such that a to the n is no, the smallest k, so that a to the k is the identity, is n. Other than 0. So r has to be 0. Okay. So, because a to the r is the identity, and r is smaller than n. So what we're using here is, if you have a generator of the group, then the only way it can generate the whole group is that its powers are never the identity until the power, the exponent, reaches the order of the group. Or in other words, the order of the element is equal to the order of the group, as we said yesterday. So for a generator, its order in the group is the order of the whole group. They're equal numbers. Did we say that yesterday?
Somewhat on the right. A subgroup is defined by its group and their existing identity. Is it that quote? I was trying to look for it.
Got it exactly what you just said. It's written down.
Yeah.
Subgroup is defined by its group and there exists an identity. It doesn't make any sense to me. Okay. But anyway, there's only
I did, yeah, we had 5 seconds, but I thought it was a good.
Anyway, this is what it is. I'll try to clarify it this way. If there are still any unclarities on Friday, we can talk about it. We don't have to do so much about the complement. What we need to do, however, is, because this is important, is theorem 4.13. So if we have a cyclic group of order n, and again, A generates the group. Then this theorem gives us the order of any element of the group. If you know it expressed as a power of the generator. So then the order of B is n divided by d. D is the greatest common divisor of K. Just okay. Yeah, so there are some. It gives you the order of this element. Okay, let's think about it. Let's take Z6. Okay, that's an example. So the order of 1 is a generator. So the order of 1 has to be 6. 6, 1, 2, 3, 4, 5, and then it jumps to 0 as its 6th iteration. What is the order of 2? Well, this is telling you that the order of 2 you get by looking at the greatest common divisor of 2 and 6, which is 2. Okay. And then you divide 6 by the greatest common divisor. So the order should be 3. And the way it works is you've got 2, next one is 4, and the next one is 0. 2 generates a subgroup consisting of 0, 2, and 4 in Z6. When you look at 3, the GCD is 3, the divisor is 2, the ratio here is 2, 6 divided by 3. So 3 generates a 2-element subgroup. 3, 0. 3 plus 3 is 0. How about 4? Well, the greatest common divisor of 4 and 6 is 2. So you should get 3 elements. So 4 plus 4 is 2, plus 4 is 0. Okay, this is how it works. So the greatest common divisor is hidden in the kind of how it cycles. Should have brought it's easy to draw this forward. And this, when you want to be there where you're. Anyway. Okay, so for the formal proof of this phenomenon that I've just been talking about, what is the order of an element? The order of an element is defined as the least number such that b to the n is the identity. Right? That was the definition of the order of an element. What's b to the m? Well, that is a to the k. So now, when you look at this position, d to the m is the identity if and only if. So therefore, because of this equality that I've just written in length, d to the m is the identity if and only if n is a divisor of k times m by that proposition above. And so this is if and only if n over d is a divisor of k m over d. So these are both integer numbers because d is the greatest common divisor of k and n. Okay. D divides k and d divides n. And that is equivalent to n over d being a divisor of n. There's a trick hidden in here. Okay. So b to the m is a to the km. By this proposition, no, the one that's just disappeared, a to the km is the identity if and only if n is a divisor of km. Now n is a divisor of km if and only if n over d is a divisor of km over d. I could just divide both by d and that preserves it. Now here, because d is the greatest common divisor of k and n over d and k over d are relatively prime. So there is no n over d in k over d. So the n over d has to be an n. That makes sense. So this is because this last one is because n over d and k over d. Okay. Now the smallest m which satisfies this, well, m greater than 0, which satisfies this, that n over d, it's a multiple of n over d, is m actually equal to n over d. There's no other. There's no smaller positive multiple of n over d than n over d. Okay. So we were looking for the smallest one, so to B to the n is E, and we found that the smallest one is an LP, which is what the theorem wanted us to say. Okay, this is it's normal that people don't understand the proof immediately. It just needs to be the cognitive process, or whatever they would say in education theory, has to happen in your mind. So you just have to process it properly. So this gives us all the generators of the N. Integers are. This is what they have to be in the end. To be relatively fine. Okay, so this theorem gives us when you want all the generators of Zn, you want all the elements of Zn whose order is n. Because the generator of the group is exactly those elements whose order is equal to the order of the group. Okay, that's what we've used it before. So the and the order is n if D is 1 and D is that, so that's it's ready. Where 1 in these groups, 1 plays the role of the generator A. Makes sense? I think so, yeah. So there is this kind of, I'm not sure in how much detail we've got this, but about these orders. So when you've got an element, okay, of any group, and we defined its order as the least value of an exponent k, such that a to the k is the identity. Okay, but the order of an element at the same time, directly from this definition, is the order of the subgroup that it generates. Because you take a to the 1, a to the 2, a to the 3, all the way, a to the order of a, and that's the identity. And these things, all these elements, all these powers of a, are exactly the elements of the subgroup generated by a. I'll just say it as a clarification, and only because I'm too lazy to start the complex groups. Wake up. Okay, so clarification. What is the order of something? Okay, so the order of a group G is S is number of elements of G. Okay? That was the definition that you probably had, I hope. Okay? That's one definition. And then what we had was And the order of A of an element in a group G is minimum all the k's which are greater than 0, and A to the k is the identity. Okay. Now, what are the powers of A? Well, A to the 1, A to the 2, 3, until you get to the order of n, and that's the identity. And then you start going again. So A to the order plus 1 is the same as A to the order plus 2 is the same as A squared, and so on. So the subgroup, you look at the subgroup generated by A is A, and so on, A to the order of n, which is the identity, and then if you continue into powering, you get back to A, provided that it has a finite order. So like the group is infinite and the order is infinite, then you can't cycle like this. If it's finite, then this is what it does. So the order of A is the same as order of the subgroup generated by A. Okay, does that clarify it? So that was something that we used, I think, in the proofs. Was a bit hesitant at that point because I wasn't quite sure whether we've covered this bit, and I don't think we did before now. But now everything's complete. Yeah, so section 4.2, which we were supposed to do, which I thought we could do, but no time. So is about complex numbers. What I'm going to do is I'll just link a YouTube video that you can watch, which explains it with nice pictures and things. So you don't worry too much about it. It's an interesting thing, but then we can't cover everything. So we'll skip that. Oh. And 4.3 is interesting if you want to do cryptography. It's got fast powers of numbers.
Is it the thing I did last week?
Yeah.
So we won't really need it. So that is kind of optional material. And yeah, next week we'll move on to, I need to get it quicker. We'll move on to permutation groups, which is quite an important topic because in some sense every group is a permutation group. In the meantime, well, there are these exercises. I thought we might start doing these exercises here, but we won't. You have two exercises to do, which are 5 and 26. So they are to be submitted by next Monday. 5 is find the order of every element in Z18. Okay, so from today, we've got plenty of information about how you find the order of an element in Z anything. And 26 is similar. And you look at this clarification. 26 asks you to prove that ZP, so the cyclic group with P of order P, where P is a prime number, doesn't have any subgroups other than trivial ones, so ZP and which kind of follows from this, so it's just a matter of putting down the ideal nesting. All subgroups of ZP are cyclic, and from that you can derive what they are by looking at what the elements of ZP can generate. Seems a bit strange to me. Okay, are there any questions? Okay, well then I'll see you all on Friday.
Oh, is it Friday? Yeah.